Hello everyone. So, we are discussing about sampling. So, in the first two lectures of sampling, I have discussed about the some theoretical part and then what is the meaning of sampling and then how much of sample we should collect based on G-wise equation, and I have briefly explained you that what are the limitation of G-wise equation. Now, this lecture we will be starting the plant sampling, that is in the plant how will you be able to collect the sample. That means, suppose I am a mineral processing engineer and I have to collect the representative samples from the running plant maybe every shift of 8 hours from different locations to monitor the performances of my different unit operations and the overall plant performance. So, before we decide that we will go for sampling, we must plan ahead. What is the meaning of planning? Now, we have to first gather some information. We must be very clear about what are the analytes to be determined. That means, whether I am collecting the sample for particle size analysis or for assay analysis or for flow rate analysis or for some other purposes. So, accordingly, your goal must be well defined for your sampling. Then, what kind of estimates are needed? That means, first the average, that means at what frequency interval you want to take the sample. That is, you want the sample from each stream on hourly basis or daily basis or monthly basis or yearly basis. So, that is very important. Or you want to do the analysis, you want to take the sample for shipment, that what quality of product I am dispatching for my client, because my prices, that is how much of money I will charge from my client, that will depend entirely on the quality and the quantity of my material. So, that quality part you are looking at. Then you have to know your sample characteristics, that is how heterogeneous is your material. So, distribution of the heterogeneity of the determinant on the lot. Let us suppose I am doing analysis for copper. So, what are the sources of copper? Is it a heterogeneous? Is it a heterogeneous source, like it may be from say sulphide mineral bearing material, also actually sulphide mineral bearing ore, it may be oxidized ore, it may be some other carbonate, or it may be mixture of all this. So, I must know that. Then it is better to have some kind of priori information, that what is the highest and lowest values. I would expect that when I am sampling your concentrate, that is what I think that I have already concentrated, and then that concentrate, the range you can have some kind of guess that whether it is within having a copper of in between 28 to 32%. Similarly, if it is tailing sample, it cannot be 28%, it has to be much less. So, whether it is around 0.02 to 0.04%, that is very important. Then we should know that is useful priori information, that is variance estimates, unit costs available. Has it been done before and have they provided some kind of your variance analysis? Then are all the necessary personnel and equipment available? Suppose we need, when we reach to the sampling point, we find that, oh my goodness, I am running short of manpower. I need someone to hold my bucket, I need someone to look at the time, I need someone to write up tags. So, whether I need 2 persons, 10 persons or 20 persons to do that. And then what kind of equipment I require? So, when you are going for sampling, you should be going there with all kind of preparedness. Then what is the maximum cost or uncertainty level of the investigation? As we have seen in the previous class, that when you want to bring down the uncertainty level, that is the precision level to be much more precise, that means the errors you want to minimize, your sample weight goes up. So, that means automatically your cost of sampling also goes up. So, how much of money I have allocated? What is the budget? So, we should have all this thing ready beforehand. Then decisions to be made, that whether we should go for manual sampling or automatic sampling. Like if you are doing the sampling for reserve estimates, you do not need automation. But if it is a processing plant and every shift you want the similar kind of your samples, probably you may think of automation, that we should have some automatic instruments or automatic equipment through which I will be able to get the representative sample very quickly. And this is also what we have already discussed, the sampling frequency, that is how frequently we need this data, we need this sample. Now, so suppose I am collecting samples on hourly basis, and suppose my plant works for 20 hours a day. So, every day I will be having 20 samples, and is my chemical analysis facility or my laboratory facility for doing size analysis are equipped enough? Do we have sufficient manpower there to generate the final data on size analysis or maybe assay analysis? So, there must be a synchronization between the two. Sample sizes based on G-wise equation, we know that if we are collecting hourly samples, say suppose each hour we are collecting 10 kilograms of samples. So, per day say suppose 20 hours running hours. So, we will be having 200 kilograms of sample. Do you have adequate space in my laboratory where the size analysis or maybe the assay analysis will be done to preserve them in a uninterrupted fashion? That means, we have to prevent them from getting contaminated and from other losses what we have already discussed. Then sampling locations. In your sitting in your office, you might have decided that okay, we will collect samples from here and there, but does your logistics support that? You might find that there you cannot have access to that, your safety officer may not allow you to do that. Maybe your equipment layout does not allow you to do that. So, we have to decide on that also, that is sampling locations. This is very important, individual versus composite samples. Like the examples I am giving, that every day you have collected 20 samples. Now, whether you want to know the assay analysis of individual 20 samples or you want the assay analysis on daily basis based on the representative samples you have collected on hourly basis. That means, you may mix up all the 20 samples you have collected of 10 kgs. So, you have got 200 kilograms, and then you want to take only one sample out of that of 1 gram for final analysis. So, for that 200 kilograms, again you have to do the sampling at your laboratory. Are you ready with that? Do you have adequate facility to do that? Is that your target, that I want assay analysis on daily basis? Then, of course, we have not discussed about that, but I have written it. So, if anybody is interested, you can look at the some of the textbooks on sampling. I would refer the GY's book. The sampling strategy, whether we want random sampling, stratified random selection or systematic stratified selection. So, only the interested readers, they can look at that. Then training. The people who will be doing the sampling, are they properly trained to do that? Do they know that how important this sampling is, and this sampling has to be done with a minimum bias. So, all this personnel should be well trained. Now, plant sampling, generally it is advised that we should do it in a moving stream. The biases or the errors will be minimum if we plan to sample from a moving stream. Even for solid materials, when they are flowing means, say suppose the material is transported through conveyor belt. So, when they are moving, we should try to sample that. That means, at the feed end or maybe at the discharge end, or even in the conveyor belt they are moving. So, even from there also we can plan to take a sample. So, the best way of sampling a moving stream of ore, concentrate or slurry is using a correctly designed sample cutter at right angle at the discharge point of a conveyor belt, chute or slurry pipe. What we try to say that if there is a conveyor belt, so you are collecting it from here and then you want to transport it there. So, you are having a conveyor belt. So, conveyor belt is now discharging the material there. So, what I try to say that when the material is being discharged to another container or to another unit, so the materials are basically free falling. So, there I should have a sampling device which will cross cut the flow. That means, the material is flowing like this and I should have a cross cutter at a right angle that should take at a frequency of the material which is being poured. And that is the example what I had shown you with the red and black particles into my previous lecture. That was the perfect example of what I have written here. That is, your cutter should be at right angle and the material how it is flowing, falling onto the next container. On the other hand, sampling devices that take only part of the stream are likely to introduce serious bias and must be avoided at all cost for metallurgical accounting. This part I would like to show you with some of the examples that what I try to mean here. See, this is what a schematic of a falling stream cutter. That means, the material is coming or say falling to another container here, which is somewhere here, and this is a sampling equipment. So, material is falling here and the cross cutter, that is your sampling equipment, should move in this way, that is at right angle, and that is the correct way of taking a sample. But say suppose this cutter is moving from only from here to there, you are assuming that whatever material is falling here, that is identical whatever material is falling here, but you may introduce some bias, because you may miss some particles which are not available here. So, your analysis may be wrong and will be wrong, not maybe. So, the first rule is that I must cut across the full stream. Do not take sample from the part of the stream. Incorrect sampling, some examples I have given. First, let us have a look at this. Suppose a slurry is flowing. Slurry, what is slurry? Is a solid liquid mixture when the particles are in very fine size ranges. Now, that is coming down through a pipeline, and many places you will find that in the plant, to make your life easier, what people do, that they punch a hole just beside the pipe and they try to bypass some of the material through this. But that is an incorrect sampling, because through pipeline, now you imagine your slurry is flowing like this and you have just put a hole here and you are trying to bypass some of the slurry. Now, you are not cutting the full stream. So, whatever material you are getting into the right side of the wall of your pipe, that may not be true representative of the entire material what it is coming down, because this side you may have different material. So, you are biased towards this right hand side of material, and that is incorrect. So, what is the correct one? That when the pipeline through pipeline, when the material is coming, the slurry is flowing, you have to have some means of taking the slurry from the slurry sample from the cutting across the whole stream. This is another example. Like say suppose I give this example, like you are asked to get a representative sample from a nearby river, and you want to do the calculation that that your analysis, that what kind of particles are suspended into that river water. A river is suppose 30 meter wide and 10 meter deep. So, it is very difficult, you will say that it is very difficult to get sample from that your middle of the river. So, what you do? You take a sample only from the side of the or the bank of the river, that is a water sample, and you are doing all sorts of analysis for your suspended solids, their size analysis, but you may have a different particles which is suspended at a higher depth and at the middle of the river than what you are getting towards the bank of the river. So, and based on your sample analysis data, you are giving a judgment that this river contains so much of material of this nature and that nature. That is incorrect. And many times what you do, you are tempted that okay, I will put a small, it is called a shark fin type of sampling, actually sample collecting device. You put it there and you collect the samples. Suppose the river is this much wide and you have put some small your sampling device to collect the sample from here. So, you are missing these samples, the slurry what is flowing through that. So, that is you are introducing biases on that. So, these are incorrect samples. This is also another example of incorrect sampling. Many times you have done everything right, that your material, your stream is coming and you are having your sample cutter in a right angle, but it is a wrong speed and wrong dimension of your sample cutter you have. So, maybe the particles are getting into your container and basically going out of your sample container because of wrong dimensions or maybe wrong speed of your container of your sample cutting devices. So, you are missing some of the particles which were supposed to be collected. This is called a reverse spoon cutter. So, this is an incorrect design because of the incorrect design. So, most automatic samplers operate by moving a collecting device through the material as it falls from a conveyor or a pipe. Like if you remember in my last lecture that I have shown a small animation how a sample cutter is moving across like this. That is an automatic sampler, and then whatever material is being collected, you are basically collecting it on a fixed interval of time. But before you install that automatic sampler, it is important to note that the face of the collecting device or cutter is presented at right angles to the stream. If it is not right angle to the flow stream, then you may be introducing some bias into that, because if it is going like this, so you are not giving equal opportunity for every particle to be collected at the same velocity at what they are falling. The cutter should cover the whole stream. That is, again and again I am saying that it should be like this, it should cut the entire stream, not like this. The cutter should move at constant speed, otherwise what will happen? Suppose I want to know the flow rate of that. So, that flow rate I have calculated that how much is the time that cutter is collecting is having for collection of samples per unit your say movement. The cutter should be large enough to pass the sample. Suppose my cutter opening can accommodate only the largest particle size of 3 millimeter, but actually in your stream you have got particles more than 5 millimeter. So, what will happen? Either they may choke my cutter opening, or maybe these particles will bounce back, they will not be collected in the cutter. We will not be able to take into consideration of those 5 millimeter particle while doing the analysis. It may be size analysis, it may be some other chemical analysis, maybe any other analysis. Now, this is generally a thumb rule, and this relationship has even been documented in some textbooks also, and it is a common practice that what should be the dimension of my cross cutter. That I said that there is a falling stream from a conveyor belt and I want a automatic sampler. So, what should be the dimension of my this cutter to avoid all those incorrect sampling related issues. So, here the velocity should be constant, as I said, and how much it should be? It should be less than to equal to 0.6 meter per second, because what will happen if it travels too fast? So, the materials may start bouncing back. So, I should have a constant speed, and that should be around less than 0.6 meter per second. It should be gentle movement. What should be the dimension of this? Now, if say suppose this is the width of that, it is represented by B, and this is the, say B0 is the aperture here. So, if D is greater than 3 millimeter, that is the D is the diameter of largest particles. That is why I said that you should have prior information about the material what you are going to sample. So, if the largest particle what I am going to sample into the stream, I ensure that it is all it is greater than 3 millimeter, then my B, that is the width of this, should be greater than 3 D. That means, if it is 3 millimeter, then my width of my sample cutter should be more than 9 millimeter. If D is less than 3 millimeter, B should be greater than is equal to 10 millimeter. That means, here if I have 5 millimeter sample, so it should be 15 millimeter or more, but if it is less than 3 millimeter, it should be more than 10 millimeter at least. So, this is the correct design of my proportional, we call it proportional sampler. This is an example of sampling smelter residues and wastes, because they are hard materials. Like smelter residues means, suppose if you go to a steel plant, you will find that there are slags. So, initially they were in molten state when they came out from your furnaces, but after cooling they have become a solid particles. So, you want to know that how much of maybe chromium we are losing into that. So, I want to do the analysis. So, what I have to do? Now, first I have to break them into very fine particles, that is what it is written, and then we should take a representative sample, and then we should go for assay analysis. So, the breakage, how will you break it, whether you have got the right kind of equipment or not, that you should be ready with. Do not make any compromise with that, otherwise your estimates should be wrong. So, we will continue this lecture in the next session also. Till then, thank you very much.